A high-impedance grounded neutral system is used to limit the ground fault current. An example is a hospital with a large number of medical devices sensitive to ground faults. The system is designed to minimize the risk of equipment damage or patient injury by limiting the fault current to a low level. Grounding impedance refers to the resistance or impedance connected between the neutral of a system and the grounding electrode. It limits the flow of fault current in the event of a ground fault, thereby reducing the voltage and current that can reach equipment or personnel. A grounding transformer is a transformer specifically designed to provide a neutral connection for a system. It can be used to create a neutral or to isolate the neutral from the transformer's primary winding. The grounding transformer's secondary winding is connected to the system neutral and to the grounding electrode. Article 250.36 covers grounding impedance location. The grounding impedance shall be installed between the grounding electrode conductor and the system neutral. Where a neutral is not available, the grounding impedance shall be installed between the grounding electrode conductor and the neutral derived from a grounding transformer. The American Electrician's Handbook defines impedance as the name given to the total opposition to the flow of alternating current. It is the combined opposition of resistance, inductive reactance, and capacitive reactance. Impedance is measured in ohms and is expressed by the symbol Z. High impedance grounding offers several advantages over solid grounding and low impedance grounding in specific applications. Firstly, it significantly reduces ground fault current. In a solid grounded system, a ground fault can result in very high fault currents, potentially causing significant damage to equipment. By introducing impedance, typically a resistor, in the grounding path, the ground fault current is limited to a much lower value, often in the range of 5 to 10 amps. This reduced fault current minimizes the risk of arc flash, equipment damage, and service interruptions. Secondly, high impedance grounding improves system reliability. The reduced fault current allows the system to continue operating during a ground fault. This is particularly important in critical facilities such as hospitals, data centers, and industrial plants where downtime can have significant consequences. Operators can be alerted to the presence of a ground fault and have time to locate and correct the problem before a complete shutdown is necessary. Thirdly, high impedance grounding simplifies fault location. Because the fault current is limited and sustained, it is easier to trace the fault using specialized ground fault location equipment. This equipment injects a small signal into the grounding system and uses a clamp-on ammeter to detect the signal on individual branch circuits. The circuit with the strongest signal is the one with the ground fault. Grounding impedance is installed between the grounding electrode conductor and the system neutral. This impedance, typically a resistor, limits the ground fault current. Where a neutral is not available, the grounding impedance is installed between the grounding electrode conductor and a neutral derived from a grounding transformer. A grounding transformer is used to create a neutral point in a delta-connected system or to provide a neutral for grounding purposes. It is a specially designed transformer that provides a low impedance path for ground fault currents. The grounding transformer is connected to the system in a zigzag or Y-delta configuration. The zigzag transformer has 3 windings connected in a zigzag pattern. This configuration provides a low impedance path for zero-sequence currents, which are the currents that flow during a ground fault. The Y-delta transformer has a Y-connected primary winding and a delta-connected secondary winding. The neutral point of the Y winding is connected to ground. This configuration also provides a low impedance path for ground fault currents. The impedance in a high impedance grounded system is typically a resistor. The resistor is sized to limit the ground fault current to a predetermined value. The value of the resistor is calculated based on the system voltage and the desired ground fault current. For example, in a 480 volt system, a resistor of 48 ohms would limit the ground fault current to 5 amps. The resistor must be capable of withstanding the continuous current that will flow through it during a ground fault. The resistor is typically mounted in an enclosure and is protected by a fuse or circuit breaker. High impedance grounding is commonly used in systems with sensitive electronic equipment, such as hospitals, data centers, and industrial plants. In these systems, a ground fault can cause significant damage to equipment and disrupt operations. High impedance grounding helps to protect equipment and improve system reliability by limiting the ground fault current. There are several types of grounding systems, each with its own advantages and disadvantages. These include solid grounding, low impedance grounding, and high impedance grounding. Solid grounding provides a direct connection between the system neutral and ground. This type of grounding is simple and inexpensive, but it can result in very high ground fault currents. Lower impedance grounding uses a resistor or reactor to limit the ground fault current to a moderate level. This type of grounding provides a good balance between fault current limitation and system stability. High impedance grounding uses a high-value resistor to limit the ground fault current to a very low level. This type of grounding provides the best protection for sensitive electronic equipment, but it can be more expensive than other types of grounding. The choice of grounding system depends on the specific application and the requirements of the system. Factors to consider include the system voltage, the type of equipment being protected, and the desired level of fault current limitation. Article 250 of the National Electrical Code (NEC) provides detailed requirements for grounding electrical systems. This article covers the types of grounding systems permitted, the methods for grounding equipment, and the requirements for grounding electrodes. It is important to consult Article 250 of the NEC when designing and installing a grounding system. Grounding electrode conductors are used to connect the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Grounding electrodes are used to provide a connection to earth. The NEC specifies the types of grounding electrodes that are permitted, including metal underground water pipes, metal frames of buildings, and concrete encased electrodes. Equipment grounding conductors are used to ground non-current carrying metal parts of electrical equipment. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device. Ground fault circuit interrupters (GFCIs) are used to protect people from electric shock. GFCIs detect ground faults and interrupt the circuit, preventing electric shock. Surge protective devices (SPD) are used to protect electrical equipment from voltage surges. SPD divert surge current to ground, protecting equipment from damage. Regular inspection and maintenance of grounding systems are essential to ensure their proper operation. This includes inspecting grounding electrode conductors, grounding electrodes, and equipment grounding conductors for damage or corrosion. It also includes testing GFCIs and SPD to verify their functionality. High impedance grounding is a specialized grounding technique that offers significant advantages in specific applications. By understanding the principles of high impedance grounding, electrical engineers and technicians can design and install systems that provide enhanced safety and reliability. Grounding is a critical aspect of electrical system design and installation. It is essential to understand the different types of grounding systems and the requirements of the NEC to ensure the safety of people and equipment. The grounding impedance is selected to limit the ground fault current to a specific value. Typical values for the ground fault current are 5 amps or 10 amps. The voltage drop across the grounding impedance during a ground fault is used to detect the fault. A ground fault relay is connected to the grounding impedance to detect the voltage drop. The ground fault relay is set to trip when the voltage drop exceeds a predetermined value. When the ground fault relay trips, it actuates a circuit breaker or other disconnecting means to isolate the faulted circuit. The grounding transformer is a 3-phase transformer with a special winding configuration. The winding configuration is designed to provide a low impedance path for ground fault currents. The grounding transformer is typically connected in a zigzag or Y delta configuration. The zigzag configuration provides a low impedance path for zero sequence currents, which are the currents that flow during a ground fault. The Y delta configuration provides a stable neutral point for the system. Grounding systems are designed to provide a safe path for fault currents to return to the source. This helps to prevent electric shock and equipment damage. The National Electrical Code (NEC) provides detailed requirements for grounding electrical systems. The NEC requirements are designed to ensure the safety of people and equipment. Grounding is an essential part of electrical safety. Proper grounding can help to prevent electric shock, equipment damage, and fires. High-impedance grounding is a method of grounding electrical systems that limits the amount of current that can flow during a ground fault. This can help to protect equipment and personnel from harm. In a high-impedance grounded system, a resistor is connected between the neutral point of the system and ground. This resistor limits the amount of current that can flow during a ground fault. The value of the resistor is chosen to limit the ground fault current to a safe level. High-impedance grounding is often used in industrial and commercial applications where sensitive electronic equipment is used. This type of grounding can help to protect the equipment from damage caused by ground faults. There are several advantages to using high-impedance grounding. Firstly, it limits the amount of current that can flow during a ground fault. This can help to protect equipment and personnel from harm. Secondly, it reduces the risk of arc flash. Arc flash is a dangerous electrical explosion that can occur during a ground fault. High-impedance grounding can help to reduce the risk of arc flash by limiting the amount of current that can flow during the fault. Thirdly, it improves system reliability. High-impedance grounding can help to improve system reliability by reducing the risk of equipment damage caused by ground faults. There are also some disadvantages to using high-impedance grounding. Firstly, it can be more expensive than other types of grounding. Secondly, it can be more difficult to install. Thirdly, it requires specialized equipment to monitor the system. Overall, high-impedance grounding is a safe and reliable method of grounding electrical systems. It is often used in industrial and commercial applications where sensitive electronic equipment is used. When selecting a grounding system, it is important to consider the specific needs of the application. Factors to consider include the type of equipment being used, the voltage of the system, and the potential for ground faults. The grounding system should be designed to protect equipment and personnel from harm. The grounding impedance, typically a resistor, is chosen to limit the ground fault current to a predetermined level. This level is typically 5 to 10 amps. The resistor must be sized to withstand the continuous current that will flow through it during a ground fault. The resistor is typically mounted in an enclosure and is protected by a fuse or circuit breaker. The grounding transformer is used to create a neutral point in a delta-connected system or to provide a neutral for grounding purposes. It is a specially designed transformer that provides a low impedance path for ground fault currents. The grounding transformer is connected to the system in a zigzag or Y-delta configuration. The zigzag transformer has 3 windings connected in a zigzag pattern. This configuration provides a low impedance path for zero-sequence currents, which are the currents that flow during a ground fault. The Y-delta transformer has a Y-connected primary winding and a delta-connected secondary winding. The neutral point of the Y winding is connected to ground. This configuration also provides a low impedance path for ground fault currents. Article 250.36 of the NEC provides specific requirements for the location of the grounding impedance. The grounding impedance must be installed between the grounding electrode conductor and the system neutral. If a neutral is not available, the grounding impedance must be installed between the grounding electrode conductor and a neutral derived from a grounding transformer. The grounding electrode conductor is the conductor that connects the grounding electrode to the electrical system. The grounding electrode is a metal rod, pipe, or plate that is buried in the earth. The grounding electrode provides a connection to earth for the electrical system. The system neutral is the neutral point of the electrical system. The neutral point is the point where the voltages of the 3 phases are equal. High impedance grounding is particularly beneficial in systems where continuity of service is critical. The low ground fault current allows the system to continue operating during a ground fault, preventing costly downtime. The fault can then be located and repaired at a convenient time. It's important to note that while high impedance grounding limits fault current, it does not eliminate it entirely. Therefore, overcurrent protection devices, such as fuses and circuit breakers, are still required to protect against other types of faults, such as short circuits. The choice between different grounding methods, including solid grounding, low impedance grounding, and high impedance grounding, depends on the specific application and the priorities of the system designer. High impedance grounding is often the preferred choice when protecting sensitive equipment and maintaining system uptime are paramount. Consider a 480-volt three-phase system. To implement high impedance grounding, a resistor is connected between the system neutral and ground. If the desired ground fault current is 5 amps, the required resistance is calculated as 480 volts square root of 3/5 amps, which is approximately 55.4 ohms. This resistor limits the ground fault current to 5 amps, protecting equipment from damage and reducing the risk of arc flash. The voltage drop across the resistor during a ground fault can be monitored by a ground fault relay. When the voltage drop exceeds a predetermined threshold, the relay trips, isolating the faulted circuit. This allows for quick detection and isolation of ground faults, minimizing downtime and improving system safety.